Welcome to Naradar Academy. In this video, we are going to discuss about inner product spaces. Let's start with the definition. For defining inner product space, you have to take a vector space along with the field F. Okay. Now you take two vectors UV from the vector space. The elements of V are called vectors and the elements of field F are called scalars. So for any UV from the vector space V, we define a product, okay, such that it has to satisfy these four conditions. We can define the product in any way. It has to satisfy only these four conditions. So what are the four conditions? The first one is the inner product of any vector with itself is always positive. Isn't it? This is true for our usual multiplication also. So when you multiply a number with itself, it will always be positive. When will it become 0? Only when the element itself is equal to 0. So this is the first property. Inner product of u with itself is always greater than or equal to 0. And it will be 0 only when the vector itself is equal to 0. Right? Then the second one is inner product of uv equal to inner product of vu conjugate. Right? Now let's talk about real numbers, then we'll come to complex numbers. In real numbers, the multiplication is commutative, no? That is a into b equal to b into a. The same way here also, in case of real numbers, inner product of uv equal to inner product of vu. But when you talk about complex numbers, inner product of uv equal to complex conjugate of inner product of vu bar. Okay, right. Then third one is like distributive property. Inner product of u plus vw is equal to inner product of uw plus vw. And the last one is like scalar product. Inner product of alpha u comma v equal to alpha times inner product of uv. Okay, so whenever you have a product which satisfy all these conditions, that space is called what? Inner product space. Okay, right. Suppose the field which we are taking here is real field of real numbers, then the inner product space is called Euclidean space. Okay, so Euclidean space means the field is the field of real numbers. And when it is complex numbers, when F is the field of complex numbers, that inner product space is called what? Unitary space. Okay, right. Now let's see few more properties. Now inner product of u alpha v equal to alpha bar into uv. See here in the definition, when alpha comes with the first vector, it is simply alpha times inner product of uv. But when alpha comes with the second vector, okay, whenever you have something with the second vector, it has to be taken outside as conjugate. Okay, alpha bar is the complex conjugate. So u comma alpha v equal to alpha bar uv. Next one is u comma v plus w. Inner product of u comma v plus w is equal to, there will be no change in this one. This is also like the distributive property. So there will be no change because all are vectors only, no. Only when you have the scalar with the second vector, it will become its conjugate. But when you have vectors, there will be no change. So this is like uv plus inner product uw. Next one is inner product of any vector with 0 is equal to 0. Right? What we say, if you multiply any number with 0, the product is 0. No? The same thing here. The inner product of any vector with 0 is equal to 0. Okay. Now we are going to define standard inner product in Rn. Okay. Rn means what? The set of all n tuple of the form x1, x2, etc., xn, y1, y2, etc., yn. So in this space, I am defining inner product of xy equal to x1, y1 plus x2, y2 plus x2, y2 plus x3, y3 plus etc. xn, yn. With respect to this inner product, this will be an inner product space, and this inner product is called what? Standard inner product. So what is standard inner product? Multiply first coordinate with first coordinate plus second coordinate with second coordinate plus etc. So this will be called standard inner product on Rn. Okay. So while doing problems, you will be given with respect to standard inner product. You won't be given with this definition. So you have to remember this. This is called what? Standard inner product over the field of real numbers. Right? Now, in case of complex numbers, okay, in Vn of C, there the standard inner product is defined to be x1 y1 bar plus x2 y2 bar plus etc. xn yn bar. That is the first vector the same. The second vector you have to take what? Conjugate. This is standard inner product over the field of complex numbers. Right? Okay. Now, next let's see one problem. Let V be the set of all continuous real valued functions defined on the closed interval 0 to 1. Okay, continuous real valued function. V is a real inner product space with inner product defined by, how do we define the inner product of fg is equal to integral 0 to 1 f of t into g of t dt. So this is the inner product. We have to check whether this satisfy all the four conditions or not. First, let's consider what is inner product of f with itself. Equal to, by definition, it is 0 to 1 f of t into f of t dt. So it is 0 to 1 f of t the whole square into dt. See, this f of t is a continuous function. We are squaring it, so it will be positive, and we are integrating it between 0 to 1, only between the two positive numbers, no? So definitely this value will be always positive. Okay, when it will become 0 only when the function itself is 0, right? So the first condition is satisfied. Next, consider inner product of fg equal to 0 to 1 f of t into g of t dt. Again, f and g are continuous functions, so we can interchange this f and g. So it is g of t into f of t dt. So this is nothing but inner product of gf. So inner product of fg equal to inner product of gf. Here that conjugate is not required because here they have given what? Real valued functions. Okay, real inner product space. So everything is real number means what? Fg, inner product of fg is equal to inner product of gf. Only when you have complex numbers, here it has to come like conjugate. Okay, right. Next one, consider inner product of f plus g h equal to integral 0 to 1. Here f plus g, no, so the first one will be f of t plus g of t into h of t dt. So now you take product of these two terms. Here this is our usual addition and multiplication, no. So here we are applying the distributive law. So f of t into h of t dt plus integral 0 to 1 g of t into h of t dt. This is inner product of fh, this is inner product of gh. Right. Next, consider the last one. Inner product alpha f comma g equal to integral 0 to 1 alpha f of t into g of t dt. So now this alpha is a scalar which you can take outside. In alpha into integral 0 to 1 f of t dt f of t g of t dt. So this is nothing but alpha into inner product of fg. Therefore, this product whatever we have defined here satisfies all the four conditions. Therefore, with respect to this product, V is an inner product space. Okay, so you can understand from this example, for any vector space over a field we can define different inner products. Okay, this is not the unique inner product, right? So we can define the inner product in different ways. With respect to this, it satisfies all the conditions, so this is an inner product space. Okay, then next problem, let V be the set of all continuous complex valued functions defined on the closed interval 0 to 1. Show that V is a complex inner product space with inner product defined by inner product fg equal to integral 0 to 1 f of t g of t conjugate dt. See, this problem is exactly similar to the previous one, except there you have real valued function. Here it is what? Complex valued function. That's the only difference, right? Now let's check the first condition. What is inner product of f with itself? Equal to integral 0 to 1 f of t into f of t conjugate dt. But what we know, a number with its conjugate z bar is equal to mod z square. So this is nothing but modulus of f of t the whole square. So modulus that itself we are squaring. So definitely this will be a positive number and it is integrated between 0 to 1. So this is surely a positive number. So when will this be equal to 0? Only when the function itself is equal to 0. So the first condition is satisfied. So for the second one, I am taking the right hand side. Consider inner product of gf conjugate. This is equal to integral 0 to 1. What is inner product of gf? Equal to g of t into f of t conjugate dt. So here conjugate is there, no? So that conjugate I am putting it here. So equal to, now you apply this conjugate over this one. Since f and g are continuous, no, so all these things are applicable here. Now apply this conjugate within the integral. So integral 0 to 1 g bar of t into, here it will be f bar of t the whole bar, no. So double time conjugate if you take, it will be simply f of t, g bar of t into f of t dt. Now let me rewrite it, f of t into g bar of t dt, but this is nothing but inner product of fg. So inner product of fg into equal to inner product of gf conjugate. So second condition is also satisfied. Compare this with the previous problem. In previous problem, what we have proved? Inner product fg equal to simply inner product gf. There, because it is the field of real numbers. Here it is complex numbers. So it has to be equal to the conjugate. Then the distributive law. right? Inner product f plus g comma h is equal to integral 0 to 1 f plus g of t into h bar of t dt. Now you multiply, so f of t h bar of t dt plus g of t h bar of t dt. This is inner product fh plus inner product gh. So this condition is also verified. And finally, scalar product alpha f, inner product of alpha f g equal to integral 0 to 1 alpha f of t into g of t the whole conjugate dt. Now this alpha can be taken outside. So alpha into inner product of fg. So all the four conditions are satisfied. Hence V becomes an inner product space with respect to the given inner product. Right. So till now what we have done, we have taken a vector space and we have taken the field. So within the vector space we have defined one product and that product is called inner product. Okay. So we have seen some of the properties. Next one is we are coming to something like our modulus. Okay, in real numbers we know what is modulus of a vector, no? In the same way here we define norm of a vector. This norm are called, otherwise called what? Length of any vector. It is defined to be square root of inner product of x with itself. This is called norm of a vector. And when this a vector is called a unit vector when its norm value is equal to 1. Unit means what? 1, modulus 1 in real numbers and complex numbers we call it as modulus, no? Here it is norm. So norm of x is equal to 1. Right. Now let's see some problems. Let V be the vector space of polynomials with inner product given by inner product fg equal to integral 0 to 1 f of t g of t dt, where f of t is equal to, so this is what we have proved as inner product space in the first problem, isn't it? Now this is an extension. Here for f of t they have given f and g, they have given particular specific value and they are asking you to find inner product of f with g and norm f. Okay, so no need to prove here. This is an inner product space, we have already proved. So for this particular f and g, what is the inner product and what is the norm that we are going to find? So inner product of fg equal to, what's the definition? 0 to 1 f of t into g of t dt. So substitute the values, t plus 2 into t square minus 2t minus 3 into dt. Now you multiply, you take the product is simply t cube minus 7t minus 6 into dt. So what is the integration? T power 4 by 4 minus 7t square by 2 minus 6t within the limit 0 to 1. So after applying the limit I am getting inner product fg equal to minus 37 by 4. Right. Next one, norm f. What is norm f square? Equal to inner product of f with itself. So integral 0 to 1 f of t into dt equal to t plus 2 the whole square into dt. So what is the integration? T plus 2 the whole cube by 3 within the limit 0 to 1. So what is the answer? 19 by 3. Therefore norm f is equal to square root of 19 by 3. Okay. Next, let's see one more problem. Find the norm of 1, 2, 3. Okay, triplet in V3 of R with the standard inner product. See, they have given simply standard inner product. What is standard inner product? Inner product of xy equal to x1 y1 x2 y2 plus x3 y3. Here it is V3 of R, so we have to stop up to third coordinate. So norm 1, 2, 3 is equal to inner product of x with itself, no? 1, 2, 3 with itself. So 1 into 1 plus 2 into 2 plus 3 into 3. So 1 plus 4 plus 9 equal to 14. So norm of 1, 2, 3 equal to what? Root 14. Right. Next problem. Find the norm of 4x plus 5y in V3 of R with standard inner product where x is equal to 1 minus 1 0 and y equal to 1 2 3. This is similar to the previous problem, but they are asking you to find the norm of 4x plus 5y. So norm of 4x plus 5y is nothing but inner product of 4x plus 5y with itself equal to. Now see, here we have to make use of this rule. Whenever you have alpha and or beta scalars with the first vector, it will be simply alpha times plus beta times. But whenever you have the scalars with the second vector, it will be alpha bar plus beta bar. That is what I am going to do. First, let me split the first vector. So it is 4x with 4x plus 5y, then plus 5y with 4x plus 5y. Okay, simply this one I have split into two parts. Next, let me split this one and then this one. So this will give you two terms and this will give you again two terms. So 2 plus 2 equal to 4 terms you will be getting. So 4x and then 4x 5y, here 5y 4x plus 5y 5y. Okay, right. This is norm 4x square and this is norm 5y square. What about this? Here we are having over the field of real numbers, no? So inner product of 4x 5y will be equal to inner product of 5y 4x. So these two are equal because we are talking we are talking about real numbers. So both are equal. So simply I can write it as 2 times inner product 4x 5y. Now here this norm is nothing but what? It is like modulus only, no? This 4 we can take it outside. This will be 4 square is there, no? So it will be 16 norm x square. This will be 25 norm y square. Here similarly this 4 and 5 you can take outside, but 5 when you take outside it will come as conjugate. Since it is a real number, its conjugate is the number itself. So 2 into 4 into 5 what? 40 inner product xy. Now so 16 into inner product xx, 25 into inner product yy, here inner product of xy. So inner product xy means what? Standard inner product only, no? So multiply coordinate wise, 1 into 1 minus 1 into 2 plus 0 into 3. So it is 1 minus 2 plus 0, right? So this will be what? Minus 40, the middle term. Let me come to the first term. Inner product of xx means what? 1 with 1 into 1 plus minus 1 into minus 1 plus 0 into 0, right? So 1 plus 1 plus 0. Similarly, inner product of y with y, what? 1 into 1 plus 2 into 2 plus 3 into 3. So 1 plus 4 plus 9. So finally, what is the answer? The norm of 4x plus 5y the whole square is equal to 342, or norm of 4x plus 5y is equal to 3 root of 38. Right. Next one, simple problem. Find the set of all unit vectors in V3 of R with the standard norm. What we have to find? With respect to the standard norm, what are the unit vectors? What do you mean by unit vectors? Norm value equal to 1. Now let me take a general vector, arbitrary vector, x equal to x1, x2, x3 in V3 of R. If its norm value equal to 1, what do you mean by that? Inner product of xx equal to 1. What is the standard inner product of x with itself? X1 square plus x2 square plus x3 square equal to 1. But what is this? This is nothing but equation of unit sphere, isn't it? With center at origin and radius equal to 1. So the unit vectors of V3 of R are only the points on the unit sphere, okay? The points which are lying on the unit sphere will be the unit vectors in V3 of R with respect to the standard inner product. Okay, now let's see two important properties. One is squads inequality, another one is triangle inequality. Squads inequality says modulus of inner product xy is less than or equal to norm x into norm y. Okay, right? So next one is triangle inequality. Norm of x plus y is less than or equal to norm x plus norm y. So these two are some important inequalities. With this I wind up. The link for the vector spaces introduction, subspaces and bases are given in the description box. If you want, you can go through that video also. Thank you.